What's up, everybody? Welcome back. I'm excited to get started on another homework set for you. Today we're going to be working with some fluid viscosity for the first time, so that's exciting. Jumping into viscosity, shear rate, and shear stress. So without further ado, let's get right back into it. So we got 3 questions we're going to try to answer today. Number 1, derive an expression for laminar velocity profile on a horizontal cylindrical tube. We'll follow that with an expression for flow rate as a function of pressure, viscosity, pipe length, and diameter, followed by, finally, an expression relating the frictional heating to flow rate, viscosity, density, pipe length, and diameter. All right, so let's get started with number 1. Derive an expression for the laminar velocity profile on a horizontal cylindrical tube. So, as we always do, let's go ahead and start with drawing a picture. So we've got a horizontal cylindrical tube, something like this maybe. And for the purposes of this problem, there's going to be a pressure difference. So we might have pressure on this side and pressure on this side. And that pressure is going to induce a force which is going to induce a flow. And for this problem, we're going to assume it's been in a steady state. So let's assume that P1 is greater than P2, meaning the flow will travel from left to right. So like this, right? Left to right. All right. And just to define some basic variables here, we're going to call this the plus x direction, and then we'll call this the pipe length, L. The pipe has a radius of R, and we need another axis. We're not going to use the y-axis. I guess we're going to use the radial axis in this from the center. So we'll call this the center, and then outward is the R direction from the center. Okay, so we have kind of this plus R and plus X. Those are axes. Okay, I think that's really all we need to get started. We're going to be deriving this expression from basic Newtonian force balance equations. So there's a few important terms that we need to define first. We have the viscosity. It's going to be denoted by mu. We also have the shear stress, tau, and then we have the shear rate, sigma. So if you see me write those down, that's what those mean. All right, so fluid's moving inside this tube. It's moving at a constant speed or constant velocity, v. And we know from the behavior of a viscous fluid with viscosity at all, that as you get closer to the surface in contact with the fluid, the velocity goes down. So our velocity profile is going to look something like this. We have the fluid traveling fastest in the center. You can call that V max, whatever you want to call it. Its velocity. It travels fastest in the center of the tube. And then as we reach, kind of the outside here, the velocity decreases down to 0 until you're practically touching the surface of the container, in which case it's 0. And obviously this happens in both directions. And so we kind of have this velocity profile that looks like that. Okay. Well, we're going to derive an expression, number 1, for that profile. So we'll do that first with a force balance equation. So, like I said, the velocity, although it's changing across the radius, it's constant throughout the length of the tube, which means it's not accelerating, which means the net force on this fluid inside the tube is 0. Okay, so we have the net force is equal to 0. So what forces are acting on this? Well, you have the forces due to the change in pressure, right? The pressure causes a force across the area of the surface there. So we have that force due to, I'll call that force due to pressure. And then we also have the force due to the viscous friction effect, right? Just call and those added together have to equal 0. Well, the force due to the pressure is pretty easy. We know from our past experience that pressure is equal to force over area. So the force is equal to pressure times area. Okay? And the pressure we're going to use here is practically the difference in pressures, right? So if P1 is greater than P2, we can say that this is going to be equal to, we have P1 minus P2, that's the difference in our pressures, times the cross-sectional area of R2. If we define the radius as capital R, then we can say that the area is pi times R squared, okay? To that, we have to add the force due to the viscous effect of the fluid. And that's going to be a force acting in the opposite direction, resisting its flow. So that's where these guys are going to come in. So we know that the shear stress still equal to force over area is also equal to the viscosity of the fluid times the shear rate. And the shear rate is equal to the change in velocity with in the x direction in this case, with respect to the change in radius. Now let's think about this term for a second. As the radius increases, the velocity decreases, right? As we get farther away from the center, radius increases, the velocity decreases. So we know this term, we're just going to keep this in mind, this term is a negative quantity. Right? So just keep that in mind. That's how this expression is going to equal 0, even though we're adding these two terms together. So we're looking again for the force of this friction. So we can take this area and multiply to the other side, and we get the viscosity of the fluid times the shear rate, okay, times the area. Well, it's not going to be the cross-sectional area this time, it's going to be the area in contact with the fluid, which is going to be the area of the cylinder. So we have, what would that be? The circumference times the length. So 2 pi r times F. Okay, and that's our force balance equation. That all equals 0. Now, this is true in general for we're using capital R right now, so the outside of the radial direction, the very extent of the limit. But it's also true for anywhere in between. So we're going to model this whole thing as we derive this expression with any radius r. So I'm going to substitute our big R with our variable r, which represents any radius on that axis. Okay. So what do we have here? Let's go ahead and simplify this, and we're going to, remember, we're looking for an expression for the velocity profile, so v. So we want to try and isolate our variable v there, and you're going to see very shortly we're going to have to do some integration. That's okay. All right, so let's go ahead and simplify this. What is P1 minus P2? Well, P1 minus P2 is effectively the negative delta P, right? We think of delta P as like P2 minus P1, so negative delta P times pi r squared. We're going to move that to the other side. Okay, so we have delta P times pi r squared equals, we'll keep this over here for now, mu dv dr 2 pi rl. Okay, pi's cancel out. R squared, R, and I think that's all it cancels out. Let's move some things around to isolate velocity. We get delta P R over 2 times the viscosity times L dr equals dV. Okay, so let's go ahead and find V. We need to integrate both sides. Okay, from this we can get, let's see, for this one, we're going to be integrating, what are we going to be integrating on? Probably 0 to R, right? Okay, so we get delta P 2 mu L, and this R becomes R squared over 2 plus C. And then this side, we get V plus C. Okay, and so we just did this straight up with the plus C's. Okay, so we can combine our plus C's, call that one constant there. We have to solve for our plus C, since we didn't use any limits of integration there. Our plus C, well, what do we know about this? We know that at little r equals r, that velocity is 0. So I'm going to write that here. At r equals r, velocity equals 0. So we can use that initial condition to solve for plus c. If we plug that in, we get delta p r squared over 4 mu L plus c equals 0. So then we get from this expression that c is just equal to negative delta p r squared over 4 mu L. Okay, great. So we can take this, plug it right back into the expression we just solved for. You'll notice it's the exact same except for our r variables there. So I'm just going to go ahead and combine those right now. We get velocity equals delta p times over 4 mu L times r squared minus r squared. Okay, so I think we've done that there. Let me just double check. Am I missing anything? I don't think so. So this is our expression for velocity. I'm going to go ahead and erase our board. We'll save that and move on to part 2. Okay, so we solved part 1, that's our expression for the laminar velocity profile. Let's go ahead and now derive from this expression another expression for the flow rate as a function of pressure drop, viscosity, and pipe length and diameter. Okay, well, we know that the flow rate, we'll use this Q there, flow rate is equal to the velocity times the area. Okay, well, we have some things changing about this situation. It's not a constant, same velocity all the way across. So what we can do here is add up all of the velocities across all the little areas, right? Sounds like an integral. So this Q really equals, in our situation, the dx. We're adding all the velocities across all the little areas. And if we look at our cross-section of our pipe, we already said that the velocity is largest in the center of the pipe, and as we get bigger in radius, the velocity goes down to 0. And as we're going to add up all these little rings, we have to define what dA is. And dA is going to be the area of one of these rings. So dA simply equals the circumference, 2 pi r, times the thickness of that ring, which is infinitesimally small, and we'll call that dr. Okay, so now we have a pretty easy expression here. Q equals the integral of v, which we just solved for v. V is our laminar velocity profile. We're going to plug that in. Delta p over 4 mu L r squared minus r squared times, now dA is 2 pi r dr. Okay, and we have our integral expression. Okay, so let's go ahead and integrate this from 0 to r. We want the total flow rate from inside out, right? All of it added together. Okay, well, we're integrating with respect to little r here, and keep that in mind. Let's drag out our constants first. So Q equals, pressure drop is a constant. We have 4 mu L, 2 and pi are both constants. Okay, and then we're left with 0 to r of r squared minus r squared times r dr. Okay, this is the same as saying, I'm just going to keep this moving over and we'll transfer the constant down in front. 0 to r of r cubed minus r squared r dr. All right, and now we can go ahead and integrate. It's pretty simple now. We get, I'm going to move over here. This integral expression is going to be equal to, carry our constant over, delta p times pi over 2 mu L. I just took that 2 and that 4, condensed it in 1/2, times the integral of r cubed is going to be r4 over 4 minus r squared times integral of r is r squared over 2. And this, of course, is evaluated on 0 to r, which yields us delta p pi over 2 mu L times r to the 4th over 4 minus r to the 4th, right? Because it's r squared. Plug in this for here, we get r squared times r squared is r to the 4th over 2, aka this is just negative r to the 4th over 4. Okay. Further simplifying this expression, we get delta p pi r to the 4th over 8 mu L. And have we answered the question? Derive an expression for flow rate as a function of pressure drop, check. Viscosity, check. Pipe length, check. And diameter. Oh, we got to change our radius here to diameter, so let's go ahead and do that real quick. That's just what the problem asks us to do. I'll do that down here. So if, what do we want to call diameter? D. So D equals 2R, or I guess I could have written it this way, R equals 1/2 D, right? So our final expression then becomes Q equals delta P pi r to the 4th power. I'm going to insert 1/2 D in there. Over 8 UL. Let's see, 1/2 to the 4th power is going to be 2 times 2 is 4 times 2 is 8 times 2 is 16. 16 times 8 is 8 plus 48 is 128. All right, so our final expression is delta P pi d to the 4th power over 128 mu L. That is an expression for Q, or flow rate, as a function of pressure drop, viscosity, pipe length, and diameter. We'll keep that one down here, and then I'll erase the board and we'll start working on number 3. Okay, number 3. From number 2, derive an expression relating the frictional heating to flow rate, viscosity, density, pipe length, and diameter. Alright, so we're introducing a new concept here, frictional heating. And frictional heating, we're going to describe using Bernoulli's equation. We're actually going to use Bernoulli's equation to kind of force all this question together. So, we've derived Bernoulli's equation in a previous video. I'm going to go ahead and rewrite it on the board so that we can remember. Remember Bernoulli's equation as change in pressure over density plus gravity times any change in height plus the change in velocity squared over 2 is equal to opposite 2. We then have change in internal energy due to over change in mass plus any non-flow work we introduce into the system per change in mass plus just kidding, minus, let's think about this, minus delta U, the change in internal energy. Yes. And this is also per unit mass, but we're just going to define little u here as C delta T. That will keep it in terms of per unit mass. Okay, so let's apply this to our problem. It's a horizontal cylindrical pipe. Because it's horizontal, we don't have any change in height, so no energy is added to our system there. We also know that it's a constant velocity of fluid traveling through the pipe. Although it changes with radius, it doesn't necessarily change with length in the positive x direction, so our velocity in the x direction doesn't change necessarily. So this is also 0. We're not introducing any non-flow related work to the system over the course of its travel on the pipe, so this term is 0. And that means we're left with this one, and this one. So we have a change in internal energy, heat, and change in pressure over density. So, frictional heating. Frictional heating is defined as the combination of these two things. Okay? And we represent frictional heating with a fancy F of that. Okay? So, I'm going to write this in terms that is a little bit easier to understand here. So we have dQdm minus delta U. So delta U is going to be the change in internal energy, which is U2 minus U1. And then this can be rewritten as dQdm, what is this, plus U1 minus U2. Okay, and this is what the frictional heating is defined as, right here. Okay, so we need to relate this back to this side of the expression, which is where the rest of our problem comes in here. So relating frictional heating to flow rate, viscosity, density, length, and diameter. So how do we include all those in this? Well, we see the change in pressure right there, and we see the change in pressure right here. And look at that, the rest of the things we need here are flow rate, diameter, viscosity, length, and density. So it all comes together. So we need delta P in terms of these variables. So we can take this equation and just rearrange this for delta P. So delta P is equal to, multiply this up, we get 128 mu L Q over pi d to the 4th. Okay, and then we also divide it here by density, and that is equal to this side of the equation, which we've described as frictional heating. Okay, and I think that's it. I mean, that describes frictional heating in terms of we need flow rate, viscosity, density, length, diameter. We got all this. So this is the answer to part 3. Frictional heating is equal to 128 times the viscosity times the length of the pipe times the flow rate divided by the density of the fluid times pi times the diameter of the pipe to the 4th power. It's a mouthful. And that's going to be our answer to number 3. So thank you for joining me on this episode of me trying to figure out fluid mechanics. And we'll join you for the next one for part 2. Thanks for joining. We'll see you next time.